Okay, welcome to the next class. This is continuing where we left off last time. What we will do today, what you will learn today is how to model the 3D space we live in and how to model the camera motion. One of the aspects in multi-view reconstruction is that you acquire images from a moving camera, and so one key element is how do you model motion of a camera. And we'll learn a little more about mathematical modeling of rigid body motion. And in that context, you will learn what a Lie group is and what a Lie algebra is. Who has heard of Lie groups before? Nobody. Oh, good. So this is a very important concept in terms of formalizing structures. A Lie group is, as you could have guessed, it's a group, but you have additional structure to that group, and transformations of the camera, they form a group in the sense that transformations can be inverted. You can always transform back to the original location. But in addition, as you can see, when you move a camera, the group has a notion of continuity, in the sense that you don't have a discrete set of elements, but you have a continuous family of transformations. You can infinitesimally move a camera, and that is one of the key elements that makes it a Lie group. And so we'll see today what Lie groups are and what examples of Lie groups we have, and also what a Lie algebra is. But let's start. So the 3D space we live in, the Euclidean 3D space, we call it E3. It consists of points in our environment. And as you know, these points can be characterized by 3 coordinates. Typically, that means you have to specify some origin, you have to specify some basis, but in that basis, each point can be represented by 3 coordinates. And so, in some sense, that Euclidean space E3 can be identified with R3 because these 3 coordinates are an element in R3. And so, often people talk about E3 and R3 exchangeably. But strictly speaking, it's 2 different things. One is the set of points in our environment, and one are coordinates in R3. And we can use these coordinates to represent points uniquely. Once we have 2 points in E3, so x and y, let's call them, we can take their difference vector, so a vector pointing from a point y to, from a point x to a point y, and we call this y minus x, this vector we call v. It's an element in R3, and that is called a bound vector. So it's a vector pointing from a point x to a point y in space. Once we remove the base point and consider it as just a vector in space that can be moved around, then it's called a free vector. So this is just to set a little bit of notation. The set of free vectors V in R3, they form a linear space, meaning the 0 vector is a free vector, and to each vector I have an inverse as well, so I can linearly interpolate free vectors and get free vectors, so this forms in overall a linear vector space. Once we identify, as we do, typically the Euclidean space with R3, we can use all sorts of things from R3. We can use the scalar product in R3 of 2 vectors. We can use the norm in R3, the Euclidean norm, and we can use metrics. We don't have to use Euclidean norms, but in practice we often do. And so with that we can compute things like distances between points, and we can compute curve lengths. So if you have a curve, and typically a curve is a mapping from some interval, say 0 to 1 to R3, so there's a curve here, and so this would be gamma of 0, and here would be a gamma of 1, let's say, and then we can calculate the lengths of that curve. The way we do that is once we have a parameterization of this curve, then we do d gamma by ds and integrate the lengths of these infinitesimal elements over the entire curve. So basically we chop up the curve into lots of little elements and compute their infinitesimal lengths. And that gives us the overall lengths of a curve. And similarly, by integration, we cannot just compute lengths of curves, but we can compute areas of, say, a surface in R3 or volumes in the same way. So if you have a surface in R3, a closed surface, you can compute how much volume is inside by integration. And what we use here, the Euclidean norms, are the norms in R3. In addition, as you know, in R3 we have what's called a cross product. So a product that maps two vectors to another vector. This is somewhat characteristic for R3, so typically for any Rn there is not necessarily such a cross product, but for R3 we have it, and this is what it looks like. It's a convention to define it in this way. There would be other possibilities, of course, but so if U is and V are two vectors with components U1, U2, U3, and V, V1, V2, V3, then this defines another vector in R3. And as you may recall from high school, where typically this cross product is introduced, when you have a vector u pointing in some direction and a vector v pointing in some direction, then the cross product is a vector that is orthogonal to both u and v. So it's normal to the plane spanned by u and v. And there is an orientation. Typically, this is the so-called right-hand rule. So if the thumb of the right hand is the vector v, u, the index is the vector v, then the middle finger points in direction of the cross product. And it's not symmetric, so v times u obviously is the negative of u times v. You can check here, if you do v times u, you see you get the inverse, you get the negative. And so it's not, it doesn't commute, that's important. Scalar products typically commute, cross products do not commute. Once we fix u, we already had that in the introduction on linear algebra, the cross product u cross v can be also modeled by applying this matrix u hat, we called it. It's a skew-symmetric matrix made up of the components of that vector u. Skew-symmetric or anti-symmetric means the diagonal must be 0 and the off-diagonals are the negative of each other. And once you apply u hat to a vector v, it mimics the same as u cross v. You can check if you apply this matrix to a vector v, you get exactly this thing up here. And that turns out to be useful because typically cross products are a little bit nasty to handle in linear algebra, but if you model them with these matrices, then they're somewhat easier. It's just a linear transformation. In turn, obviously, every skew-symmetric matrix in the 3×3 matrices corresponds to the cross product with some vector u. It's obvious because if I take any skew-symmetric matrix, it must have this form, and then I can read off the three components of the vector u. So obviously, there is a one-to-one correspondence between vectors in R3 that I use for a cross product and these skew-symmetric matrices. And in fact, one can then say we define this operator hat that takes a vector in R3 and maps it to a skew-symmetric 3×3 matrix. And in turn, of course, we can have an operator which is called V often, and that operator does the inverse. It takes a skew-symmetric matrix and maps it to the real, the three-dimensional R3 vectors. The space of skew-symmetric matrices, 3×3 skew-symmetric matrices, is called SO3. Little SO3, mind you, not big SO3. We had big SO3. We'll get to that in a second. The special orthogonal group, the rotation matrices. This is little SO3. Why we use the same letters here, we'll see that in a second. And the connection, I can say it up front, is that large SO3 is a Lie group, and little SO3 is its corresponding Lie algebra. What that is, as I said, we'll get to that in a bit. We already talked about rigid body motion, and when I first introduced it, I said rigid body motion is rotation and translation, is what you can do with the camera. You can translate it in space and you can rotate it. There is a different way to introduce rigid body motion that is a little bit more close to the term rigid body motion. What rigid body motion really means is that you want to move a rigid body, and that means that the length of vectors is preserved. So if you have 2 points on your object and you do a rigid body transformation of that object, these 2 points have a distance that remains the same. If the distance between a pair of points changes, then the motion is no longer rigid, then it's non-rigid. But rigid body motion means, in particular, the length of vectors has to be preserved, and in addition, it means the cross product of vectors has to be preserved. So if I take 2 vectors and their cross product, before and after transformation, it should be the same. This is a very different way to define rigid body motion. I didn't talk about rotation, I didn't talk about translation. All I say is any transformation that preserves lengths and preserves the cross product is what I call a rigid body transformation. The question, of course, is how is this definition related to the earlier one, rotation translation? And in fact, we can show, I'll show you on the next slide, that these two constraints imply that it must be rotation and translation. There is no other transformation that preserves lengths and cross product. But before I show you, I wanted to mention a few more things. Interestingly, once you fix what it does, once you specify that it has to preserve lengths and that it has to preserve the cross product, it implies that it also preserves the scalar product. This is not quite obvious, but interestingly, once you have the lengths or the norm, you can extract the scalar product from it. See, once for any vectors I have defined the norm, I can say u plus v squared minus u minus v squared, the norm squared. If you calculate that, you remember this gives u squared minus u squared, v squared minus v squared. And then I get 2uv plus 2uv is 4uv divided by 4 gives you exactly the scalar product. So I can actually, once I have the norm, define what it implies what the scalar product is. This is called the polarization identity. It gives a relation between norm and scalar product. And so if the norm is preserved, then also is the scalar product. And once I have the cross product and the scalar product preserved, it means that also the so-called triple product is preserved under the rigid body transformation. The triple product, I think in German it's called Spatprodukt, if I'm not mistaken. It's this product basically with 3 vectors, u, v, and w. It is u scalar product with v cross w. And that is preserved because the cross product is preserved, and as we saw here, the scalar product is also preserved. So if I transform these 3 vectors and then do the triple product, it's the same. Why is that interesting? Well, the triple product, as we see it here, denotes volume. You may remember that from high school. If you have 2 vectors, let's call them u and v, then let's call them v and w to stick with that notation. So the cross product of v and w is a vector in that direction, and if u is somewhere here, this is u, then these 3 vectors span a volume element. And the amount of volume in that block here is exactly this one. So the volume in here is given by U scalar multiplied V cross W. That is the volume. And so when I say the triple product is preserved, it means rigid body motions in particular also preserve volume. Meaning if you take a rigid body and you move it around rigidly, it will have the same volume after moving. And you know quite well, if you do some non-rigid motion of an object, you distort it, you change lengths, you change orientations, you change angles, then you typically also change the volume. So if you take a sponge and compress it, it's not a rigid body motion. But rigid body motions preserve lengths and preserve the cross product, and we saw here that implies they also preserve the scalar product, the triple product, so they preserve lengths and volumes and etc.
Excuse me.
Yes.
I think I didn't get this, how the triple product is related to one.
Oh, I didn't, yeah, so how it is related, I didn't actually say, but if you take three vectors and generate this triple product, what you get is the volume spanned by these three.
Yeah, I got confused by the drawing because the cross product between W and V generate a vector that is orthogonal.
Yes.
It generates the same vector U.
Oh, in this setting, yes. But let's say these are not orthonormal. They can be like this, and then U can be like that. So you have V, W, and U here. That still defines some kind of volume. I'm not a good drawer somehow. Yeah, you can imagine that this sorry. Yeah, so you get some volume that they span essentially, and that block, that volume is exactly this. So if you take the unit vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 as three vectors, and then create their cross product, then you get 1 as a solution, because the volume spanned by these three is exactly 1. So the volume of this block is 1, but if you take any other vectors, the volume may change. In particular, if V and W are parallel, then the volume they span is 0, right? And you can see that V cross W, if they're parallel, that actually gives you 0. And so, I don't prove that this is the volume, but it's a fact. Yeah. Or if the vector U is in the same plane as V and W. So if U, this is just sanity checks, but if U and V and W are, they span some plane. If U lies in the same plane, there's no volume. The way you can see that is V times W is orthogonal to that plane. If U is in the plane, the scalar product is 0. So the volume is. So these are various sanity checks that indicate that that does make sense. So we see that rigid body motions preserve volume, and we define them here by saying they preserve lengths and cross product. Any transformation that preserves lengths and cross product is a rigid body transformation. What I'll show you now is that this actually leads to rotation and translation the way we saw earlier. This is not uncommon in mathematics, that you can define terminology in various ways, and then you have to typically show that one is equivalent to the other. One definition is equivalent to the other definition. Here, for example, the question is, does this definition of rigid body motion, saying it must preserve lengths, it must preserve cross product, is this definition sufficient to define a specific representation of what a rigid body motion looks like? A definition that we can then actually work with. And it turns out, yes, that is sufficient. So here's the argument. If the transformation, let's call it GT, so that is our transformation, T, because we consider a certain time T, we'll get to that later. So GT is our rigid body motion. And now we say it has to preserve lengths, it has to preserve cross product. Basically, that means if it preserves lengths and cross products, it means that we have to only specify for our basis what it does to that coordinate frame. So we define we have a coordinate frame consisting of some origin and 3 vectors defining our space. And if we say how the transformation affects that basis, then for every other point it's specified because the lengths must be preserved. So we can define any point with respect to this frame, and then if we know how the frame is transformed, we also know how that point is transformed. And so all we need to specify in a rigid body motion is what it does to the frame. And that means what does it do to the origin, and the origin we can move it around randomly, so we call that T is a translation, 3 degrees of freedom to move the origin. And then we have the frame spanned by, say, 3 orthonormal vectors, E1, E2, E3. And their transforms we call Ri. That's the transform of EI, so that is the new basis vector after rigid body transformation of the old one. In addition, now we said scalar product and cross products are preserved. That means if I take the scalar product of 2 R's, Ri times Rj, it must be the same as EI times EJ. And if we assumed in the beginning this is an orthonormal frame, so then if E define an orthonormal frame, then the R's also define an orthonormal frame. So they're also orthogonal. Delta ij, remember, is an expression that is 1 if I equals j, and 0 if I is not equal j. And so we see if the E's are orthonormal, then the transformed frame is also an orthonormal frame. And in addition, if they are oriented, E1 times E2 is E3, E1 cross E2 is E3, then we also have the same for the R's. R1 cross R2 must be R3 because the cross product is preserved. So an orthonormal frame in that orientation stays orthonormal in the rigid body transformation. This we have guaranteed. And what does that actually mean? If these vectors, say these columns R1, R2, R3, if they are orthonormal, it basically means that the matrix R that is made up of these 3 vectors is an orthogonal matrix, i.e. R transpose R is the unit matrix, or R transpose is the unit matrix. The second property, that they're oriented in this fashion that R1 cross R2 is R3, implies that the determinant of that matrix is +1. Remember, if I have an orthogonal transformation, then the determinant is automatically either +1 or -1. I have either rotations, or I have in addition a mirroring if determinant is -1. If the orientation is preserved in the rigid body motion, it means the determinant must be +1, meaning the matrix R that is spanned by these 3 vectors is indeed a rotation matrix, a matrix that is orthogonal and determinant +1. And as you may recall, this group of matrices, invertible matrices, which are orthogonal and determinant +1, we call them the special orthogonal group, SO3. And so overall, this shows that the rigid body motion, GT, can indeed be written as rotation of some vector x plus translation. Because that's all I can do to the frame. I can shift it, I can move it, and we saw this motion must be a rotation motion. Otherwise, I don't preserve a scalar product and cross product. So we see we have a rigid body motion here. And the rigid body motion can indeed be written as rotation times translation. So what you've seen now is you can either introduce rigid body motion by saying this is rotation and translation, but sometimes that loses the intuition why that is called rigid body motion. And the rigid body motions are called rigid body motion because they preserve lengths and because they preserve cross product. So angles are preserved. If you take two vectors and they have a certain angle, you do a rigid body transformation, the angle stays the same. And the volume stays the same. All of these things are preserved, and this is the case if and only if you have rotation and translation. We will now look at the rotation matrices a little more closely. As I said, you can rotate around a certain angle, you can rotate back. These rotations form a group, but in addition we can do what's called infinitesimal rotations. We can take our camera or whatever and rotate it infinitesimally, little by little. And with every rotation we get a new element from the rotation group. This is not always the case for any group. Remember, if I take, for example, one of the simplest groups is the integers, and together with adding as a concatenation operator, this is a group, but it's not an infinitesimal. It's not a group where I can move infinitesimally from one element to the next, because I have a discrete set of elements. Here I have a continuous group, a group where I can move continuously from one element to the next. And so this is what we will actually do. We will look into infinitesimal rotations. Why do we do that? Well, the reason is that rotations are a bit nasty to represent. If you draw this group, it's a group that has the rotations have 3 degrees of freedom, but it's not a linear space. Meaning, if I take two rotation matrices R and R tilde, and I sum them, typically what I get is not a rotation matrix. And so you can represent rotation matrices, but the nasty thing is, we saw it on the previous slide here, these constraints that they have to be orthonormal and that the determinant has to be +1 are not very nice to implement as constraints. In general, the determinant is a bit of a nasty thing to handle. Why is that important? Well, let's say you have images and you want to estimate how did my camera move? How did it rotate? Then you have to say, well, let's define a rotation matrix. So that is a 3 by 3 matrix that in principle has elements A, B, C, D, E, F, G, H, I, let's say. 9 elements. But I cannot choose them freely because most choices will not give you a rotation matrix. I have to choose these elements in a way that the matrix is orthogonal and that the determinant is +1. So now imagine I want to do an optimization where I want to determine these parameters that define my transformation of the camera. Then in the optimization I have 9 degrees of freedom to estimate, and I have very nasty constraints that these 9 parameters have to fulfill. I assure you, you don't want to do that in practice. It's not very nice to implement. The product, yes, but not the sum. The product is a rotation matrix, yeah, that's right, but not the sum, and that means in terms of summation, they don't form a linear space. So often you can abstractly write the fact that the rotation matrices, SO3, form some curved space. You're right, if I multiply rotations, then I'm still in the space of rotations, but not if, with respect to summation, you're not in a linear space. And so what we want to do is we want to find a better representation of these nonlinear spaces. And this is, in mathematics, this is called a manifold, and a group that is at the same time a smooth manifold is called a Lie group. We'll get to that in a second. So what we do is we consider a family of rotations parameterized with some parameter t. So t is like time, if you want. And what we consider now is that we have our camera and we move it around over time. And then we look at points in space. And we consider the transformed points. X transformed at time t is the rotation applied to the original. So if you want, you can think of this as the coordinates of point x original at time t when I consider coordinates with respect to the current camera frame. Then in the original frame they have the coordinates x original, and with time they get new coordinates. In particular, if r at time 0 is the identity matrix, then at time 0 these are the coordinates of my point, and once I move the camera the point doesn't actually change, but the coordinates with respect to the camera change because the camera rotates. RT for any time t is a rotation matrix, so an orthogonal transformation matrix with a determinant +1, and that in particular we have this constraint: R times R transpose is the unit matrix for all times t. If this is true for all times t, you may remember from analysis, if an expression in time is constant over time, it means the derivative with respect to time must be 0. And so we can deduce, if all these matrices for any time t are orthogonal matrices, that implies that d by dt of this R transpose must be 0. And if we apply the derivative to this expression here by the derivative rules, we get dr by dt, so the dot is just the time derivative here. It's a shorthand notation, so this is dr by dt times R transpose plus R times R dot transpose. You may remember, if you do derivatives of a product, you have the derivative of the first times the second plus the first times the derivative of the second. And so we can deduce that this expression here must be 0. And if we bring one of these terms to the other side, it means R dot R transpose is minus R dot R transpose transposed. This is just rewriting the same thing. Why is that interesting? It's interesting because it tells us that if R is a family of rotation matrices, then this expression here, R dot R transposed, is a skew symmetric matrix. So all of a sudden, once we do derivatives here, we end up with skew-symmetric matrices that appear. And this is why the skew-symmetric matrices play an important role in modeling rigid body transformations, in particular modeling rotations.
Why do we get 0 when it takes derivative?
This is a fact from analysis. If you have a function f of t that is constant, and then you do d by dt of this expression of f of t is d by dt of a constant, and a constant, the derivative of a constant is 0. And the constant is here indeed, yes, it's the identity. And it's the same identity matrix for all times. So the derivative of the right-hand side here is 0, and the derivative of the left-hand side is this here. So we see R dot R transpose is a skew-symmetric matrix. And that in 3 by 3 matrices means there is a vector W for each time t in R3, such that R dot R transpose is W hat. The hat operator being just that skew-symmetric matrix associated with W. And then if we rewrite this expression, remember R transpose is nothing but R inverse, because it's an orthogonal matrix. So if we multiply from the right with R, we get R dot equals W hat times R. So in other words, just knowing we have a family of rotation matrices, R of t, implies that R dot must be equal to W hat times R with some skew-symmetric matrix W hat. This here, by the way, is called a differential equation. It's an equation that links the family of rotation matrices we consider with its derivative, R dot. In addition, we have assumed that this family is such that at time 0 we have the identity, so R of 0 is the identity. And so if we plug in 0 here, it follows that R dot at time 0 is nothing but W hat at time 0. And so in other words, that skew-symmetric matrix W hat of 0 is a first order approximation of rotation. And this is actually what we're doing here, is we're looking at that Lie group, SO3. It's not a linear group. In particular, in that group we have the identity matrix I. And now what we're doing is we have a family of rotation matrices that it lives in that SO3 space, and at time 0 we are here, and so we are saying, how does the rotation change? Remember, R dot is dr by dt. How does R change with time? What is the change in rotation? And that basically means what we're looking at is the tangent space. We take the derivative at the unit matrix at 0. And that tangent space is by construction a linear space, and it is defined by these skew-symmetric matrices. And so what we see is that this is the Lie group, SO3, Lie group. It's a nonlinear space. And this is the corresponding Lie algebra called little SO3. The Lie group are the rotations, orthogonal matrices determinant plus 1. The Lie algebra are 3 by 3 skew-symmetric matrices. And these skew-symmetric matrices form a linear space, so if you sum them, they stay skew-symmetric. You can do linear combinations and you stay in that space. And once you have an infinitesimal rotation, so now we're looking at the rotation not at 0, but just ever so slightly away from 0. So at time 0 we have an identity transformation, and a little bit further, so R at time dt, where dt is an infinitesimal time step, in a first order expansion we can say it's R at time 0 plus a change in rotation, and that change in rotation is nothing but dr by dt times dt. dr by dt is this W hat times dt. And so we see that change in rotation is nothing but a move in the direction of the tangent space, in direction of W hat. And the whole intuition behind doing this is that the skew-symmetric matrices that form this tangent space, called the Lie algebra, they are a linear space, and this is the space that is much nicer to work with. So what you can do is you could define elements in the Lie algebra, and they are all of this type. They all have the diagonal 0, and they have some elements in the off diagonal and the negative of this on the other side. So there is your 3 degrees of freedom of your rotation space. We said rotations have 3 degrees of freedom. That's why we have a 3 here. And here are these 3 degrees of freedom. If you model rotations directly with 9 elements and then the constraints that they are orthogonal and that the determinant is +1 is very nasty. But if you model them with skew-symmetric matrices, you have 3 degrees of freedom here. That's your 3 free parameters. You can choose them. And then you get an element here, and there is a corresponding element on the Lie group. And this is how you can model and estimate rotations, and this is what's usually done to estimate camera motion, is that you work in the Lie algebra space, because it's a linear space. And that means I have 3 explicit degrees of freedom that I can optimize, and I have no additional constraints. Usually optimization under constraints is a very nasty business, in particular if these constraints are ugly, like the determinant of something must be something. Here, once I use the Lie algebra, I have no constraints. What we will see in the next slides is how we can get from the Lie algebra to the Lie group. How, for any element in the algebra, we get a corresponding element in the group. What is the rigid body motion, or the, in this case, rotation associated with some skew-symmetric matrix. So here a little more about the definitions. So what we saw here is in the above calculus is that in infinitesimal rotation, so I have a family of rotations at time 0, they're the identity. I move just ever so slightly away from 0. This is an infinitesimal rotation, and this infinitesimal rotations can be represented by skew-symmetric matrices. Again, down here, a rotation by dt is nothing but an offset from the unit matrix by some scaled version of W hat of a skew-symmetric matrix. Yes?
Wouldn't that mean that every rotation matrix has only ones on the main diagonal?
No, not exactly. This is just an infinitesimal first-order approximation. The way you can actually see that, maybe to relate it to something you've already seen, consider rotations in the plane. And as you may remember from high school, these rotations can be written as matrices cosine theta, minus sine theta, sine theta, right? You may remember that representation. For theta equals 0, I get the unit matrix. Now assume I have a very small theta, so not 0, but close to 0. That's infinitesimal. What can I do? I can do a Taylor expansion of all these terms. And what I get is cosine theta is 1. And then the next term is in theta squared. So I can drop that. And sine theta is the first order expansion, just theta. And so this is nothing but the unit matrix plus minus theta, theta, 0, 0. And that's a skew-symmetric matrix. So you see that in some sense, the Taylor approximation to these rotation matrices gives you the unit matrix and some skew-symmetric offset. But in practice, of course, once I do higher order expansions, then I get terms of theta squared here, etc. And here as well. Right, but if I neglect higher order terms, then into a first order approximation, the change is just a skew-symmetric matrix. In planar rotations, you don't typically need to revert to the whole concept of skew-symmetric matrices and Lie algebras, because you have 1 degree of freedom and you can choose that degree. It's your parameter theta. But when you have 3D rotations, then you have more parameters, and then you cannot write things as compactly as here. And then it helps to have this understanding of the Lie algebra structure. So here again the definition. These rotations are called a Lie group, and the skew-symmetric 3×3 matrices, this tangent space to the Lie group at the identity, is called the Lie algebra. So here again, the definition, a Lie group, sometimes it's called an infinitesimal group, is a smooth manifold that is also a group, or a group that is also a smooth manifold. So we exploit the fact that in addition to rotations forming a group, because I have a neutral element and an inverse element to each rotation, I can invert things. In addition, they have this infinitesimal notion that I can move through that space of rotations continuously, and I always get a new rotation. And I can compute derivatives, so I can say how does the rotation matrix change with time, and this implies that what I have underlying is a manifold structure. And more specifically, a Lie group is a group such that the operations multiplication and inversion are smooth maps. And what we showed above is that the tangent space at the identity of the rotation group is little SO3, the Lie algebra of skew-symmetric matrices. This concept of Lie group and Lie algebra is a very general one. It holds for any Lie group, so for any group that is also a smooth manifold. Here we have it for the rotation matrices, but there are many other Lie groups. That said, one should say that the SO3 is the most commonly encountered Lie group in sciences. This is, I believe, where things started, where the whole notion of Lie groups and Lie algebras was invented. And we will see in a second that even the terminology stems from these Lie groups. But it can be applied to other groups. The two Lie groups that we will study in this class are the rotation matrices, SO3, and the special Euclidean group, rigid body transformations, SE3, that is rotation and translation. Yes?
The big SO3
yes.
curve itself, the condition that it has to be a group, does it mean that it has to be something like a circle or a sphere?
No. No. This may look like a circle or a sphere. No. In fact, this drawing is slightly misleading. This space has dimension 3. So it's not a one-dimensional space. It's not a 2, but a 3-dimensional space. And it doesn't look as nice as a circle. If it was, then there would be some more elegant parametrization. Yes. So this is why I don't have such a drawing in the slides, because drawings are helpful, but they're also misleading. What this is supposed to show you is that this group is continuous. I can move from one element to the next, and it's supposed to show you that it's not a linear space. Meaning if I take two rotation matrices, one here, one there, and take their average in that embedding space, then what I get is not in the Lie group anymore. It's not a rotation matrix in general.
How accurate is this approximation?
With the Lie algebra? It's maybe approximation is the wrong term. Basically, the Lie algebra is the tangent space to the identity. Any group has an identity element, a unit element, and if it's a Lie group, I can define derivatives and tangent spaces, and so I can always construct a tangent space at the identity. And for any Lie group, the tangent space at the identity is called the its corresponding Lie algebra, and that is an exact construction. It's a derivative. The next question is what you mean. To what extent is this approximation still consistent with that rotation? That's a good question, actually. We'll get to that. we'll get to the question of how can we map from a skew-symmetric matrix here to its rotation matrix. And there is such a mapping. Maybe just for those who have never heard the term algebra before, I guess there's different, you have encountered it at some point in mathematics. An algebra over a field is a vector space, but with an additional structure. In a vector space, you can add, you can do summations, you can do scalar multiplication. In addition to a standard vector space, the algebra also has a multiplication of elements on that vector space. So some multiplication that maps two elements of that vector space to another element of the vector space. And this mapping, this product is called the Lie bracket. And here it's just defined by two matrices, skew-symmetric matrices in this case, and then you take the product of these two matrices minus the commuted product. So W hat times V hat minus V hat times W hat. And you can check this actually is a skew-symmetric matrix that you get. It's not difficult to check that this is a skew-symmetric matrix that you obtain in this way, and this is called the commutator. In general, matrices, as you know, do not commute, so in general, this is not zero, the difference of these. So W hat times V hat is generally not V hat times W hat. But what it always is for skew-symmetric matrices, this is also a skew-symmetric matrix. And so this is called the Lie product or the Lie bracket or the commutator. There's different names for that. So that's in general an algebra, and this is why the skew-symmetric matrices, they're a linear space, they're a vector space, but you have this additional product that you can define, and that makes them an algebra. This is actually the guy who invented the whole concept of infinitesimal group transformations, who studied this, who derived the mathematical formalism, who saw that if you have rotations, that they are not only a group but a manifold structure, and that it is much better studied in terms of its tangent spaces, because the tangent spaces are linear spaces, and that's much nicer to work with. Interestingly, a Norwegian-born mathematician. Norway is not a huge country, at least in terms of population, and this is maybe one of the most prominent mathematicians from Norway. He was in Norway most of his life. He actually later came to Leipzig in 1886, succeeding Felix Klein, another famous German mathematician, but then he went back to Norway towards the end of his life. And he had a groundbreaking paper which he called Theory of Transformation Groups, published in 1893. And so there he argues that you should use the Lie algebra to model group transformations like rotations. How do we get from the Lie algebra, if we use the Lie algebra to model rotations, how do we get back to the Lie group? This is a transformation that we will study now, and it is defined by the so-called exponential map. So the map from here to here is modeled by the exponential function. Why that is, you will see in a second. It's actually not so difficult to see. We saw earlier that if we have a group of rotation matrices, and at time 0 we have the identity matrix, we saw that they can be represented by this differential equation. That is, the change of r at time t is given by w hat times r. So So let's assume W hat is some skew-symmetric matrix. Then we can try to solve this equation system. So let's say I give you this equation system and I say I want a family of rotations such that at time 0 there should be the identity matrix, and such that in addition they should fulfill this equation. And that actually uniquely determines these matrices, because if I say what the first order derivative is, it basically tells me from every time step to the next, how does the rotation matrix change. This is what I define here, is the change in the rotation matrix from some time to basically the next time step. And you can solve the differential equations. There's a lot of techniques to do that. This is actually a particularly simple differential equation system. It just means the change of some quantity is proportional to the quantity itself. This is something that you encounter frequently in nature. It is an exponential decay or exponential growth process. If the change in a quantity is proportional to how much you have at time t, then you have always some exponential law. And you can validate that, so you can easily show that this is the solution, e to the power of w hat times t. I say it's easy. Something you may not have encountered frequently is an exponential of a matrix. So e to the power of a matrix. I don't know, have you seen that anywhere? It's actually not so different from using standard exponential mapping. The way the exponential map is defined, x for any x is given by sum over n equals 0 to infinity, x to the n over n factorial. That's the definition of the exponential map. And of course, you can do that for matrices as well. Powers of matrices, if they're square matrices, you can do exponentiation easily. You can do. So this is, if you write it out, it is the unit matrix plus x squared over 2 plus etc. Right, and this is actually, again, you see the first order approximation is then 1 plus the skew-symmetric matrix. So here I wrote it down again. This is the definition of the exponential function applied to w hat times t. And you can check, if you insert that into this expression, it solves your equation system. At time 0, e to the power of 0 is 1. So that is fulfilled. And if I take the derivative with respect to time, then the exponent w hat comes down and I get w hat times r of t. So that clearly solves the equation system. And what we see is the function that maps from the skew-symmetric matrix w hat in the Lie algebra here to the rotation matrix is the exponential function. Just applying the exponential map gets me to the corresponding rotation matrix. So that is very nice. That way what I can do is I can model rotations in this fashion by modeling skew-symmetric matrices, 3 by 3 skew-symmetric matrices. I can explicitly, have 3 degrees of freedom that I see there. And then if I want the rotation, I just apply the exponential function. What this actually models is a rotation, r, around an axis w by an angle of t. That is, if the length of the vector w is 1, then t is the amount I rotate, and w itself is a vector that defines the rotation axis around which I rotate. There is, of course, different ways to represent things here. For example, we had the scalar t, that is the angle of rotation, and w here is then the axis of rotation. But of course, you can absorb t into the skew-symmetric matrix. Then this is no longer of unit lengths. but then you can say the rotation is exponential of some skew-symmetric matrix V hat, where V hat is nothing but T times W hat. So there's different ways to represent that, but in short it basically means I can get from the skew-symmetric matrices to any kind of rotation by e to the power of W hat. And this is why the transformation from the Lie algebra to the Lie group is called the exponential map. It's called the exponential map because for rotation matrices it is an exponential map. Interestingly, for other Lie groups and Lie algebras, this is still called the exponential map. So the map from the algebra, the Lie algebra, to the Lie group is always called the exponential map. Even if for general Lie groups, it's not strictly speaking an exponential function. And this shows you that the whole notion of Lie groups and Lie algebras was actually built on the rotation matrices. That's where the terminology came from. This is why this map is called the exponential map. And we'll see in a second something you may remember. There is an inverse to the exponential function. Anyone know what that is? The logarithm, right? So I can invert that. I can get back from the group to the algebra by the logarithm. And there as well, you can apply logarithms to matrices. Interestingly, you don't often do that in analysis classes, but all of these functions, exponential, logarithm, they all have some Taylor series representation or some representation as a series, and that can be easily applied to matrices. Easily is maybe not quite right. The question is, how do you do these different powers of matrices? Do you actually have to compute matrix powers, etc.? In practice, generally not. We'll see that there is a more elegant way to write things. But so for now we've seen the mapping from the Lie algebra SO3 to the Lie group, large SO3, is done by exponentiation. And in turn, as I said, we can do the inverse, we can apply the logarithm, and that gets us from the Lie group SO3 to the Lie algebra, the skew-symmetric matrices. And that way we have a way to associate rotation matrices with skew-symmetric matrices. How this logarithm is done, we'll see that here. We can define an inverse function to the exponential map. In the context of Lie groups, this will lead to a map from the Lie group to the Lie algebra. So that means for any rotation R in SO3, there exists some W and its corresponding skew-symmetric matrix W hat, such that the rotation is nothing but exponential of W hat. The question is, how do I find that? How do I find such a W? This is then denoted as logarithm of R. So the inverse to the exponential function. And here is a constructive way to get this W. And I must admit, I'm not going to prove that this is a good choice for W, or this is a choice that actually fulfills this. So we want an element, some skew-symmetric. Let's say someone gives you a rotation matrix, 3 by 3 rotation matrix, and says, find me the skew-symmetric matrix that models this rotation, in the sense that X of W hat should be R. And this is how you can construct it. So assuming that you not have the identity, if you have the identity, then you just take 0, of course. X of 0 gives you the identity. If you don't have the identity, you can do this. You can, the length of the vector W is given by the trace of that matrix R minus 1 over 2 and the inverse cosine. And the vector itself, so the axis of rotation is given in this fashion, where these are the different elements of the rotation matrix. Yes?
Is there some
This is exact. This is exact. So if you take this vector w that you get in this fashion, then exp of w gives you exactly r. Again, I'm not going to prove that this is actually fulfills this. You can try that in, I think we may do this in the exercises, that you actually try to calculate that. So what that statement says, that for any orthogonal transformation, any rotation SO3, so orthogonal and determinant plus 1, we can realize this transformation by rotation by an angle norm of W around the axis that is given by W over norm W. So this unit vector defines the axis of rotation, and the length of that same vector defines the angle around which you rotate. And in fact, that statement is not quite obvious, and it was never clearly intuitive to me, that no matter how you rotate a camera around, once you have rotated it, you can represent that rotation by a single rotation axis and a certain degree around which you rotate an angle. But that is basically what this states. Give me the rotation matrix and I can construct the rotation angle and the rotation axis in this fashion. So that turns out to be rather useful, actually. You can see if someone gives you a rotation matrix that you can construct automatically the rotation axis and the angle. One thing that is important when you work with exponential maps and logarithms is there is no uniqueness in general. As you know, if I take the same angle of rotation and add 2 pi or multiples of 2 pi, multiples of 360 degrees, I get the same rotation. You know, if I rotate around a whole circle, a full circle, then it doesn't affect things. And so obviously there's an infinitely large family of equivalent representations. So there is not a unique W hat to model a rotation, but there's a whole family of equivalent rotations. And this is typical also for the real numbers and the logarithm, that you have not always uniqueness. We saw that you can realize the rotation by taking a skew-symmetric matrix W hat and exponentiating it, and I can represent any rotation in this fashion. So that's good. That means if I want to estimate rotation matrices, it suffices to estimate some skew-symmetric matrix. And for any skew-symmetric matrix, for any rotation, there is a skew-symmetric matrix that models it. But what we have to do, we saw, is to exponentiate it. And in practice, you don't want to actually compute powers of matrices forever. You know, if you do this, one of the key drawbacks in numerical implementation is, of course, the little infinity up here, right? I don't want to take products of matrices and yet another product and then never end, you know, and then it's always be some approximation only. It turns out there is a closed form formula that you can use. And it's a bit similar to, you may remember that from complex analysis, e to the I phi can be written as cosine phi plus I times sine phi. The way you derive this equation is actually quite simple. You plug it in here. If you plug that in here, then you have e to the I phi is nothing but sum over I phi to the power of n over n factorial, n equals 0 to infinity. And then if you expand that expression, you always see I get even and odd powers of I. The even powers are real numbers, the odd powers are imaginary numbers, and if I separate them, I get some expression plus I times the imaginary part. And if you and that's actually usually used as a definition for sine and cosine, that the real part is called the cosine, So all of these components that are the even powers of phi, they are called cosine phi, and the odd powers are called sine phi. And in a similar fashion, you can do that with matrices. So if you have a matrix here, W hat, and what we do here is we separate the norm. Well, we'll get to that. You can show that for a skew-symmetric matrix W hat, the exponentiation of that matrix can be written in this way. So it turns out from these infinitely many powers that you have to compute in principle, in practice you only need to compute W hat and the square of W hat. And then things just iterate and you get the same. Basically W hat cubed is then again proportional to the unit matrix, etc. Sorry, the cube is proportional to the matrix itself. And so you have the unit matrix, the skew-symmetric matrix, the square of that skew-symmetric matrix, and the rest are just real numbers. This is the length of the vector, this is the length squared, and then sine and cosine appear. And this formula to calculate the mapping, this exponential map applied to skew-symmetric matrices, this formula is called the Rodrigues formula. And so that formula happens to be quite useful in practice because it allows you to compute that exponential map in closed form. And I actually decided to sketch the proof. It's a bit compact, so again, for some of the results in the class, I sketch proofs, but the proofs are rather compact often in the interest of time. But what I recommend is that you go over these at home on your own and try to derive the proofs yourself. That actually turns out to be very useful to actually understand things, is to do calculations on your own. I highly recommend that. You know, calculating things actually makes you better understand the structures. What you can show, let's say we have a skew-symmetric matrix of unit lengths. So we take any any vector W, the length of it we call T, and we divide out the lengths here. So V is the normalized skew-symmetric matrix. So that is the skew-symmetric matrix where these three elements form a unit vector. So we divide out the lengths, and if we do that, then for this normalized skew-symmetric matrix, one can show that V hat squared is nothing but VV transpose minus the unit matrix. You can just try it, and you will see that this is indeed the case. And V hat cubed is nothing but minus V hat. And that should remind you of the same property for the complex numbers. If you have the complex, the imaginary I cube is nothing but minus I. Same thing. And so, interestingly, we have exactly the same property for V hat. In fact, there are ways to represent complex numbers. Instead of having this weird I as the square root of -1, you can also use skew-symmetric matrices to model complex numbers. It's a different representation. Because what's essential about the complex numbers is exactly this reproducing property, that if you take cube of that quantity, you just get the negative of it. And so if you do that, you can imagine you can separate those terms that are proportional to V hat squared and those terms that are proportional to V hat. And you see the V hat cube is again proportional to V hat. And so if you take this whole exponential function here and all the powers, you can just arrange them into those that are proportional to the unit matrix, this one, those that are proportional to V hat and to V hat squared. And you don't see other powers because the higher powers are again just proportional to these three, to one of these three terms, or or they have elements that are proportional to these three terms. And if you do the calculations right and you separate the terms properly, you see that you get unit matrix, and then you get these terms times v hat, and these terms times v hat squared. And then if you look closely, what you have here is nothing but the sine of t. T being the length of your skew-symmetric matrix. And what you have here is nothing but 1 minus the cosine. And so then, if you insert v hat as being w hat over norm w, you see that you get exactly this expression here. So that is the Rodrigues formula. So in addition to having an exponential map from the Lie algebra to the Lie group, we now actually have a way to compute that map in closed form. And so if you want to model rotations, you have some optimization problem. See, in practice, the way you have to look at it, once you have to solve practical problems like estimating the rotation of a matrix, you have some cost or quality function, typically called E, and then you have your rotation matrix, R, and then you want to optimize that. So you want to minimize this, you want to find the best rotation that minimizes some cost. But the problem is, if R is in SO3, how do you solve this minimization? Do you take 9 parameters and then say, well, the determinant has to be something? You don't typically do that, but what you do is you rewrite that as E of R of W hat, or we can actually write E to the W hat, and then we minimize over W hat. So we have some expression, some cost or quality criterion, which is now parameterized in our skew-symmetric matrix, and we just have to optimize over skew-symmetric matrices, and that strictly means we have W in R3. We have 3 parameters that we have to optimize for, such that this cost as a function of these parameters gets minimized. And this is how in practice you do camera pose optimization. You don't take 9 parameters to represent your rotation. That would be terrible. I mean, you can do it, and people have done it, but it's not the smartest thing to do. And instead, what you use is this Lie algebra. So you actually work in the Lie algebra, and when you want to read out your rotation, you just do the exponential map to get to the corresponding rotation matrix. But for doing that, you need to have a way to compute that mapping. And this is where the Rodrigues formula is helpful.
In the previous slide, you said we have a problem with the default of 2pi, right?
Yes. Yes. What you can expect, so the question is, what is the issue with this non-uniqueness in the optimization? This is an issue. It means that there is no unique solution W to solve your problem. There are many equivalent solutions that give you the same rotation matrix and therefore the same cost. And so for every optimal solution to this, I can immediately tell you infinitely many equivalent solutions. Just if you add rotations by 2pi, doesn't change things. But in practice, that's not usually that is not an issue. There are sometimes issues where you want to have a more unique representation. And there are many ways to represent rotations. There are also the so-called quaternions. I decided not to talk about these in class, but these give a somewhat less ambiguous representation. For our purposes, though, it doesn't really matter if you have multiple possible solutions, as long as we find a good one. Now we come to the special Euclidean group, and what we will see is that basically the same idea that we apply to rotations, namely the idea of taking the tangent space and modeling the elements in our group by corresponding elements in the tangent space, we can do the same for the special Euclidean group, rotations and translations. So we have the exact same thing that we have here, SE3, the special Euclidean group, and then little SE3, the corresponding Lie algebra. And in fact, the rest of the plot remains exactly the same. We have a unit element in the special Euclidean groups, that is a unit matrix for rotation and translation 0. That's our unit element, and we can define a tangent space. So there is just a slight generalization here, but the whole idea, the concept is exactly the same, that now in addition to rotating the camera, we allow for translations as well. But again, you can imagine we can do things infinitesimally. We can translate infinitesimally, we can rotate infinitesimally. This group can be written in this way, so either rotation translation in concatenated, or if you like to use homogeneous coordinates, then you can write it as a 4×4 invertible matrix consisting of a rotation matrix here, translation, and then 0, 1. So that is, we talked about it earlier, is the embedding of the special Euclidean group SE3 into the 4×4 invertible matrices. They model translation and rotation of the coordinate frame and of the space, and that way we can model the camera motion. And again, like in the rotation case, what we now do is we consider an infinitesimal family of transformations. Let's call them GT, having an a family of rotation matrices, translations over time, 0, 1. So we assume that the camera moves continuously, and for every time step we have some rotation and some translation. Again, like in the rotation case, we consider the expression g dot times g to the minus 1. Since we have a differentiable family of transformations, we can compute dg by dt. And if you do that for this, you can show that dg by dt times g to the minus 1 looks like that. So again, I skipped the calculations here, but this is rather straightforward to show that this looks like that. And so what we see here is that g dot g to the minus 1 has up here r dot r transpose, and we saw earlier that this is a skew-symmetric matrix. And this is then typically some vector in R3. So in general, we can show, if we define that vector here, we just call it v of t, we see that g dot times g to the minus 1 is of this form. It's a matrix such that the lower row is 0, and in the upper right left-hand corner we have a 3×3 skew-symmetric matrix, and here we have some three-dimensional vector. And these matrices, these 4×4 matrices that we get in this way, they are called psi hat, and they're called the so-called twists. And so these actually form the Lie algebra little SE3, that is the twists. You see they're almost the same as the skew-symmetric matrices, but in addition there's a 3-vector here, three-dimensional vector appended, and then 2 zeros to make it a 4×4 matrix. Why is that useful? Because you see again, if we take g to the minus 1 to the other side, then we see that g dot is equal to that matrix times g. So this is what we have, I guess, on the next slide. Now here, g dot is psi hat times g. So we just multiply with g from the left-hand side, and then we get g dot is psi hat times g, where psi hat is this twist matrix. Psi hat is called a twist. Why is it called a twist? Because twisting means that you rotate and translate at the same time. And in infinitesimal, rotation and translation is called a twist motion. So we can see this 4×4 matrix psi hat, the twist here, is nothing but a tangent vector along the curve GT at the origin. So we again take the tangent space at the origin, and it's spanned by these matrices psi hat. So whereas we saw for the rotations, the tangent space is spanned by these skew-symmetric matrices, here the tangent space corresponds to these twist matrices that are of this form: skew-symmetric matrix in the upper left corner and some 3D vector here. And so that space of twists, 4×4 matrices of this structure, is called the Lie algebra, little SE3. So that is the Lie algebra corresponding to the Lie group large SE3. So very much in the same way as for rotations, we can construct the tangent space for rigid body motions. And this is yet another Lie algebra, and this is little SE3. And this is common terminology that if you have a group, a Lie group, the large letters are for the group and the small letters are for the corresponding algebra, the tangent space. And again, we can define these operators had and v, this is called v, to convert between the coordinates of the twist and the matrix. You see the coordinates we have here, the skew-symmetric matrix has 3 degrees of freedom. That vector here has also 3 degrees of freedom. So in total, this is the thing I should have changed when changing the drawing. The dimension of these spaces is 6 here. And so the plot is even more misleading. It's not a 1D curve and this is not a 1D plane, but both of these spaces have 6 degrees of freedom. And the 6 degrees of freedom are the 3 rotational degrees of freedom and the 3 translational degrees of freedom. And so we can now define operators that take these 6 degrees of freedom, v and w, v the vector here, w being the 3 components in the skew-symmetric matrix, and make out of it the twist. So that is a mapping from R6 to these twist matrices, and in turn we can take any twist matrix and extract the parameters, the 3 parameters of the translation and the 3 parameters associated with infinitesimal rotation. And that gives us the 6 degrees of freedom. So when we do camera pose estimation and we want to estimate both rotation and translation, we can use this expression. We can have 6 parameters to represent our problem, and then we have this twist matrix psi hat and the exponential map to give us the rigid body motion. Here's how you get the rigid body motion out. I guess at this point I will stop. And I will finish tomorrow about how to get from the Lie algebra to the Lie group and back. Thank you.